All right, we're going to talk about linear independence and fundamental solution sets. In this lesson, a lot of your intuition from linear algebra will hopefully carry over. So, two functions are said to be linearly independent if neither is a constant multiple of the other. In other words, like 3x and x, those are linearly dependent because the first one is 3 times the second one, but sine x and cosine x, those are linearly independent. And a set of functions is linearly independent if none of them can be written as linear combinations of the others. So, for example, e to the ix, e to the minus ix, and cosine x, those are linearly dependent, since cosine x can be written as a linear combination of e to the x, e to the ix, and e to the minus ix. But cosine x, sine x, and x are a linearly independent set. And we just use this vocabulary that for an nth order linear homogeneous ordinary differential equation, n linearly independent solutions are said to form a fundamental set. And to put this in linear algebra speak, it's just like saying in an n-dimensional space, it takes n linearly independent vectors to form a basis. It's the same thing. I think of a fundamental solution set kind of just being like the differential equations speak for a basis. Okay, so the linear algebra example is that in R2, 1 comma 0 is not a basis because that only lets you kind of reach points on the x-axis through its span. And 1, 0 and 2, 0 do not form a basis because the second one is 2 times the first one, but 1, 0 and 0, 1 do form a basis. And there are certainly other bases for R2, right? An infinite number of choices. Similarly, for the equation y double prime plus y equals 0, sine t is not a fundamental set of solutions because it's a second order linear equation, and we know that it takes two linearly independent solutions to form a fundamental set. Similarly, cosine t is not a fundamental set. But cosine t and sine t are a fundamental set because they're both solutions to the differential equation, and they're linearly independent. Similarly, e to the it and e to the minus it are a fundamental set. Why? Because they're linearly independent, and if you plug them in, they're both solutions to the differential equation. And we can go on like this. 7e to the it and 2e to the minus it. Those form a fundamental set. Right? So just like there's lots of different choices you might be able to make for a basis in linear algebra, lots of different choices you can make for a fundamental set of solutions to a linear homogeneous differential equation. All right, thanks for listening.